Grüezi miteinander. Do I get 100 points if I do it in Swiss German or? Oh, okay. So I'll go for the 50 points. So my Rump session is about fuzzing. So well, let's do it like that because I don't have slides at hand. You have demos. Does it? No. Does it work? Yeah. Excellent. This is a function. And, well, do you want to spot the bug, or is it obvious? Okay. So it parses messages, and it will just allocate, it's a type length value, length value message, so it will get the length from the message, and then allocate the buffer and mem copy into it. So it's basically crashing if you provide the random inputs, but the issue is that there is a signature that is verified in the beginning. This is the main function that is just calling the parser. Nothing is here. And so we can just generate a random message. And okay. And this is a message, so you can see the signature, you can see the length, and then the message. And if I do something like that, it will extract the message and print it. So what if you want to find bugs in that software by fuzzing? So this is how to compile it. This is what people were doing in the past. So basically they were just having random inputs and call the target with a random message. But of course it's not going to work. Okay, because it's only it's only looping through 10 times and providing random messages, and it doesn't find any bug because in any case the signature is invalid. So since you're all doing maths, I guess you can infer the chance of hitting the right signature from 10 chances out of 2 power 16 different, but there's the birthday paradox maybe happening somewhere, but this is not the point. So how many of you have heard about AFL? Oh, excellent. So AFL is a fuzzer that is basically, it has smarts, and it compiles the target with a specific version of GCC that is instrumenting the file, and then it would modify the inputs to make sure that all branches are taken. And then if you just AFL GCC the target, and then you start fuzzing, without, let's do it. Okay, oh my god, shit. Unprepared demo, alarm. I think I have, this is the only thing I have to do. Okay, so this is expected. It says, oh, but you didn't provide any sample data, so there's nothing to mutate. But since the fuzzer is really smart, you just have to go into messages and provide any random data as a start and retry up. And then it will see that A doesn't work because it chokes on the verification, first byte verification. Yeah, that's it. I hope it's going to find a crash. Normally it takes like a few seconds, but yeah, it found a crash. So if we go into findings, we can see that the fuzzer was able to, from the input we gave, he modified the input file and found out that the first byte needs to be C and S, and then by hitting a random value here that is bigger than the actual buffer, it will actually trigger the crash. But everybody knows about AFL, so I came here to talk to you about something new, and new is always better. So, do you know about libfuzzer? Oh, wow, awesome. So for all the others, there is a project from one of the LLVM core developers, and it's called libfuzzer, and basically it's integrated into the LLVM compiler. So the only thing you have to do to use it is to write this kind of function. So it's predefined name, LLVM fuzzer test1 input, and it will just LLVM will provide the data on the side. I mean, it's like the input buffer that LLVM will provide. And the only thing that you have to do is make sure that the target function is called with this particular buffer as an input. So you just have to do this, and then, libfuzzer. So what this script is doing is actually compiling with clang and adding coverage. So this is what AFL is doing, but then with LLVM it's integrated as a command line option. So you can just get coverage for each edge inside the program. So each time there is a jump, you can see which branch is taken. And the other option is for using address sanitizer, which is an option that would detect even the slightest out-of-bound access. Like even if you're trying to read 1 byte beyond the buffer that is allocated in valid memory, it will detect it. And then you just have to run the generate target. So it's compiling, and then here the crash is found instantly. So what it says, address sanitizer has detected a heap buffer overflow, and this is located 1 byte. And you can so I don't know why I don't have colors, but usually it's colored. So it says here is the heap layout, and the offending byte is located here. So with AFE is the left of the red zone, so the danger zone and everything. Wow, it's nicely integrated. And why is this better? Because AFL is basically running your app with a command line that is the target file. But with LLVM further, you can actually call any function inside your app. So imagine you have a very complex document processing software, and you have the source, but you don't really want to launch the full software every time you open a document. You just want to fuzz this particular function that is actually rendering the SVG images inside the document, for instance. And then you just have to write this LLVM test1 input function calling the SVG parser, and then you could actually fuzz directly. And the speed of the execution is like hundreds to thousands times better than just launching the full suite with a test file. So I hope you've learned something today. And I was the last, so I'm not sure who's taking the mic next. Do you have questions in the middle?